This is the first lesson in the nature of chemical reactions unit. In this lesson, we will look at our first learning goal, collision theory, and more specifically, the first success criterion A for that learning goal. So learning goal 6.1 says, I understand the collision theory of reactions, and the success criterion we will focus on here today is success criterion A. I can explain the collision theory of reactions at the molecular level. So a question that we're going to ask here is, how do chemical reactions occur? In our learning so far of chemical reactions, we've simply said that a chemical reaction or a chemical change is any process where we get a new substance formed. But the question is really now, how does that actually happen? How does one substance or more than one substance turn into a new substance? Well, let's consider a simple reaction where we have hydrogen gas reacting with iodine gas to form hydrogen iodide. And notice the balancing of the equation here. We need two hydrogen iodide molecules to form from one hydrogen and one iodine molecule, because those are diatomic, hydrogen and iodine. If we were to draw some sort of sketch of these molecules, that might look something like this, where the hydrogen, again, is two atoms because it's diatomic, so I'm going to use these red atoms here to depict a hydrogen molecule, and reacting with an iodine molecule, and iodine's a larger atom, so notice I show that here, and I'll represent those as blue. And then our products, we get two separate hydrogen iodide molecules, where each of them has one hydrogen atom and one iodine atom in the molecule. So my question is how do we go from these two separate hydrogen and iodine molecules to these two molecules that can each contain one atom of hydrogen, one atom of iodine? Well, the answer comes from the collision theory. The collision theory tells us that reactant particles must collide in order to form products. So in other words, these molecules, the hydrogen molecule and the iodine molecule, they have to run into each other in order to get these products. So there's more details to it than just that. But one thing you might be wondering is, well, how do I get molecules to collide? These things are tiny. How do I make sure they run into each other? Well, you have to remember, if you had even a small container where you mix some hydrogen gas and some iodine gas, we're talking about billions of molecules. And these molecules, they're going to be distributed throughout the container. So it might look something like this. This is a small schematic here where, again, my red molecules are the hydrogens, my blue are the iodine. And these molecules, just based on their random motion, and they are moving all over the place. Notice my blue arrows here representing the motion of the iodine molecules, my red arrows representing the hydrogen molecules. They're going to run into each other all the time. Yes, sometimes hydrogen will run into hydrogen and iodine will run into iodine, but there will be other collisions where the hydrogen and the iodine molecules run into each other, just based on their random motions. So we will have all sorts of collisions happening. And that's the case anytime you mix any substances. There's going to be all sorts of collisions between the particles that are certainly occurring. Now here's the trick, though, and here's where some of the more detailed things come into play, is that most of these collisions, even the ones that are between a hydrogen molecule and an iodine molecule, most of these collisions do not result in product formation. And the reason for that is there are two stipulations that have to be met in order for these collisions to form products. So one of them is that the particles must collide with the correct spatial orientation. In other words, the atoms have to line up correctly in order to get the products. So I have a couple of scenarios for you here. So let's say one scenario is where the hydrogen and iodine molecules collide like you see here, with the atoms lined up like this. And the second is they collide more, I guess you might call this head to head, where this is more side to side, this is more head to head. Now recognize this, these are just two possibilities of the nearly infinite number of ways that there would be. Because, for example, if we rotated this molecule just 1 degree one way and this one 1 degree another, or if this molecule was more side by side like this one, and this one was rotated just a little bit. So it's not as if there's only two possibilities. There are millions and millions and millions of possibilities for how these things collide. but just giving you two things to think about in your head here. Ask yourself this: which of these two orientations is more likely to give us this? In which scenario do the atoms line up more correctly in order to form these products? So if you just look at the orientation or the direction of the molecules, you'll see that this second possibility is the one that lines up best. The reason being is if these two molecules collide this way, the hydrogen atom that's on top can line up with the iodine atom on top, and that would form this molecule here, and the same is true with the ones on bottom. Whereas if the molecules collided like this, more in a side-by-side fashion, then the atoms just don't line up right in order to transition to these products. And so we can see that the orientation, the direction of the molecules matters. Now, in this very simple example, it's pretty easy to see. The point of this is not to be able to look at pictures of molecules and be able to figure out exactly how they have to collide in order to form products, although if you just look at the shape of the molecule, we can often figure it out. The point is that simply to understand that the direction matters, that these particles, they have to run into each other in the right way in order to give us products. Okay, so that's one stipulation that has to be met. The other stipulation is that the particles, they have to collide with enough energy in order to break bonds that already exist. In other words, the particles have to be moving fast enough. So if we go back to that scenario where we said these particles have to collide in this head-on fashion like we see here, if the particles aren't moving very fast, or if they're moving really fast, we'll have two different outcomes. So if they're not moving very fast, I'm representing that with these shorter arrows, all that's going to happen is the molecules just bounce off of each other because there's not enough energy in the collision to do anything. It's like if you just have a small bumper-to-bumper hit with your car, most likely nothing's going to happen if you're not going very fast. But if you're going fast enough, now we can break these bonds. So these bonds that exist between the hydrogen atoms and the iodine atoms, those can get broken, and now we have products formed based on the energy of that collision. Okay, so we've seen two different stipulations here that have to be met. At this point, I want you to pause the video and complete the check for understanding number 1 there on your note sheet. And once you've had a chance to completely answer it, then play the video and go to the next part. All right, you've had a chance to do check for understanding number 1, and I will take a look at that in class whenever we're back the next day. So the second question I want to ask here is, why is a minimum amount of energy required? Okay, why do we have to have a certain amount of energy in order to get this reaction to happen? Well, if we think about the changes in the molecules, and this diagram here I'm showing it a little different. I'm specifically putting a line in here between the atoms to represent the bond that's bonding those atoms together. So I have a bond holding the hydrogen atoms together. I have a bond holding the iodine atoms together. And notice our products, those bonds, those aren't there anymore. Those bonds holding the hydrogens and the iodines together, they no longer exist. So the point is this: the bonds must be broken. We have to have energy to break those bonds. Actually, that'll be something we come back to and study a lot more in the next part of our unit here, our next learning goal. But we have to have energy to break those bonds. This leads us to understanding the term activation energy. And you can see here the symbol for that, capital letter E for energy, and then the subscript A, meaning energy of activation. Activation energy is simply the minimum amount of energy colliding particles must have to start a reaction. In other words, the minimum amount of energy needed to break bonds. Now recognize this is a minimum amount of energy. The particles could collide with more than this amount of energy and the bonds would still get broken, but there is a minimum amount. Just like there's a minimum amount of energy required to break somebody's bones. Okay, not that I want you to go to try to break anyone's bones, but if you simply hit someone on the arm with a mild tap, you're not going to break their arm. But if you haul off and whack someone as hard as you can, if you hit them in the right spot, you just might break someone's arm if there's enough energy there. Again, I wouldn't recommend trying that. So notice this: before, our bonds are between the two individual hydrogen atoms and the two individual iodine atoms. After the reaction, we now have bonds that are formed between one hydrogen and one iodine. Well, what's this going to look like in between? Do the bonds just magically change which atoms are bonded? The answer to that's no, because it's an entirely different bond. It's not as if this bond moved between these atoms and this bond moved between these atoms, or vice versa. During the collision, or in other words, in between the reactants and products, we have this kind of intermediate or transition state that looks something like this, where we have partial bonds. That's what these dotted lines are representing here. We have these partial bonds where the old bonds that were there are starting to break. The new bonds that are going to form are starting to form. We call this the activated complex. Okay? The activated complex is the transition state that exists between reactant and product particles, where old bonds are being broken and new bonds are being formed. So again, going back to our diagram here, these old bonds that did exist, they're starting to get broken. The new bonds that are going to exist in our products are starting to get formed. And the only way we get to that is if the particles collide with this minimum amount of energy, called the activation energy. So these two terms work hand in hand. We need that minimum amount of energy to break bonds, and because we're breaking the bonds, we can form the activated complex, which is this transition state between reactants and products, where old bonds are getting broken, new bonds are starting to form. All right, please take a second and complete the second check for understanding on your note sheet. All right, so you've had a chance to do that. This is the end of the lesson, actually. I just want to take one last look at the learning goal and success criteria. So our learning goal 6.1, I understand the collision theory of reactions. And on this particular lesson, we were only looking at a single success criterion. I can explain the collision theory of reactions at the molecular level, which was the point of all of this discussion.